Hello dear student, I am Hrishikesh Labhade, working as an assistant professor at Srimati Vimla Ben Khimji, Tejokaya College, Devrali Camp, Nasik. In today's lecture, we are going to learn about alkyl halides. This topic includes in Savitribai Phule Pune University's second year BSc semester first course. So let's get started. In last lecture, we discussed about IUPAC nomenclature of alkyl halide, type of nucleophilic substitution reaction and elimination reaction. We also studied the preparation of alkyl halide from alkene and alcohol, and also discussed about hydrolysis reaction, nitrite and nitro formation reaction, isonitrile formation and famous Williamson's ether synthesis. Session agenda. In today's lecture, we are going to learn about nucleophilic substitution reaction, Sn1, Sn2 and Sni with its mechanism, energy profile diagram, stereochemistry and kinetics. We end our session with the elimination versus substitution, in which we discuss about nature of substrate, nature of leaving group, stability of alkene formed, solvent polarity and temperature that affect the product of elimination and substitution reaction. Learning objective. From today's lecture, student can understand nucleophilic substitution reaction with its mechanism, its energy profile diagram, stereochemistry and its kinetic. Student can also draw energy profile diagram of substitution reaction. Students are able to write the mechanism of nucleophilic substitution reaction such as Sn1, Sn2 and Sni. From today's session, student will understand on what factor does the substitution and elimination product are formed. Nucleophilic substitution reaction. Substitution reaction involves the attack by a nucleophile. The reaction is referred as Sn. S stand for substitution and N stand for nucleophile. The hydrolysis of halide by aqueous NaOH is an example of nucleophilic substitution reaction. Here we see the general reaction where Rx is an alkyl halide as a substrate and OH is a nucleophile, which gives us product as alcohol ROH and a leaving group halide. The nucleophilic substitution reaction are divided into two classes. Sn1 reaction. Sn1 stand for unimolecular nucleophilic substitution. When the rate of nucleophilic substitution reaction depends only on the concentration of alkyl halide, the reaction is first order and represented by Sn1. S for substitution, N for nucleophile and the 1 represent unimolecular nature. The example in this category is the hydrolysis of tertiary butyl bromide by the aqueous base such as NaOH, KOH to yield tertiary butyl alcohol. This involves the substitution of weaker nucleophile bromide by a stronger nucleophile hydroxide. We see the corresponding reaction in the image given below. Kinetics. Rate of the reaction depends upon the concentration of tertiary butyl bromide, that is, it is a first order reaction. Rate is equals to K1 and in bracket the concentration of substrate, that is alkyl bromide here, where K1 is a first order rate constant. Now we will discuss a mechanism of a Sn1 reaction. The reaction takes place in two steps. Step 1 is the formation of carbocation or a carbonium ion. The first step is a slow step and involves the heterolytic fission of CBr bond to form a tertiary butyl carbonium ion as an intermediate, which is stabilized by inductive effect of 3-methyl group. The bond breaking step requires high energy and hence it is a slow step and rate determining step. The carbonium ion is a sp2 hybridized. It is planar in nature and have a bond angle of 120 degree. Step 2. The attack of nucleophile. The second step is a fast step and it involves the attack of nucleophile or a solvent molecule on the carbonium ion. As the carbonium ion is planar, the attack of nucleophile can occur from both sides. That is, it is able to attack from front side as well as from back side, resulting in the formation of tertiary butyl alcohol. If we start with an optically active substrate, The product obtained due to backside attack and frontside attack would be enantiomer of each other. Here in this image we can see the mechanism of the corresponding reaction. Tertiary butyl bromide is the bromide is lost as a living group behind a sp2 hybrid carbon of carbocation which is planar, and the nucleophile OH- can attack from front side as well as from back side, giving us a 2 enantiomer. This is energy profile diagram of Sn1 reaction. Energy profile diagram is a graph of potential energy versus the reaction coordinate. Here there are two peaks showing the formation of carbocation. The potential energy is on y-axis and the reaction coordinate on x-axis. The reactant is get converted into stable product with a less energy, and intermediate is carbocation in this case. Stereochemistry. Stereochemistry is a branch of chemistry in which we study molecule in 3 dimensions. The stereochemistry of Sn1 reaction is racemization. The Sn1 reaction involves the formation of planar carbonium ion which is attacked by nucleophile from the front side as well as from the back side. If we start with an optically active substrate, the attack should result in the formation of pair of enantiomer in equal proportion and should therefore be racemic. In practice, however, 100% racemization is not possible. Most of the Sn1 reaction occurs with a varying degree of inversion. Example: R1 phenyl ethyl chloride on hydrolysis with aqueous NaOH gives 75% S1 phenyl ethyl alcohol, that is the inversion product, and 25% of R1 phenyl ethyl alcohol, which is a retention product. Here we can see the 100% racemization is not observed. Here we can see the mechanism of the discussed reaction. 25% R enantiomer and 75% S enantiomer is formed. The Sn1 reaction mechanism, it is found that all Sn1 reaction with a higher proportion of inversion than the retention. Higher degree of inversion indicates that even though an intermediate carbocation is planar, the chances of backside attack of a nucleophile are more than the front side attack. This is due to 2 factors. One is stability of carbocation and second is the nucleophilicity of a solvent. Now we will go to the Sn2 reaction. Sn2 stands for bimolecular nucleophilic substitution reaction. When the rate of nucleophile substitution reaction depends on concentration of both the substrate, that is alkyl halide, and a nucleophile, the reaction is second order and it is represented by Sn2, where S is for substitution, N is for nucleophile, and 2 represent biomolecular nature of the reaction. The example in this category is the hydrolysis of methyl bromide by an aqueous base such as NaOH, KOH to yield methyl alcohol. We can see the corresponding reaction in the image given below. Now we will study the kinetics of the reaction. The kinetic study of the reaction showed that the rate of reaction is proportional to the concentration of alkyl halide, that is substrate, as well as the nucleophile. Approach in nucleophile is it follows the second order kinetics. We can see the rate equation. The rate is directly proportional to substrate and nucleophile, and then we will replace the directly proportional sign by equal sign by substituting a constant K2. K2 is a rate constant second order. So final rate law is rate is equals to K2 substrate concentration multiplied by nucleophile concentration. Here in this case the substrate is methyl bromide and nucleophile is OH- hydroxide ion. The overall rate of the reaction depends on the slow step of the reaction known as rate determining step. Bond breaking is in general expected to be slow step as it is endothermic and requires input of the energy. On the other hand, the bond formation step is fast step and it is exothermic in nature. Mechanism. It is a one-step process involving one transition state as an intermediate. The formation of COH bond and breaking of CBr bond takes place simultaneously. Thus the bond making and bond breaking are concerted process, that is they both takes place simultaneously. The rate of the reaction depends on the concentration of CH3Br and OH. Thus the breaking of CBr bond and formation of COH bond taking are a slow step. Ingold proposed that the nucleophile OH attacks the carbon atom from the front side of the CBr bond, from the back side of CBr bond. The formation of COH bond and breaking of CBr bond takes place simultaneously. The energy released in the COH bond formation is utilized for the breaking of CBr bond. Here we, in this image we can see the mechanism of the Sn2 reaction. The nucleophile approaches from back side of the leaving group. This is slow step reaction, and we will get inverted product alcohol, methyl alcohol, with a Br minus as a leaving group. Here one question arises, why the nucleophile is approaches from the back side, why backside attack is happening here. The nucleophile OH approaches from the back side of the CBr bond because there is a minimum steric formation interaction and it requires minimum energy. If OH approaches from the front side, that is from the same side of Br, there will be a lot of steric hindrance and dipole repulsion, as both of them have same charge and requires higher energy. That's why the front side attack is not possible in Sn2 case, and a backside attack with the inversion of configuration. Transition state. As OH approaches the carbon atom, a weak bond is formed between OH group and the carbon atom. At the same time, the CBr bond is gradually weakened, giving rise to a transition state. In transition state, the carbon atom is bonded to 5 group. The OH group and the Br are located as far as possible. The 3 hydrogen atoms are in one line, in one plane, with a 120-degree bond angle between them. The leaving group bromide and the nucleophile are in the plane perpendicular to the 3 hydrogen atoms. Since the rate determining step involves the collision of 2 species. Energy profile diagram. It is as we discussed, it is a plot of potential energy versus the reaction coordinate. The reactant are on higher potential energy and product are on the lower potential energy, which are that's why the product are stable. Here we can see the one peak in the transition state showing the formation of intermediate. Stereochemistry, inversion. In the Sn2 reaction, the configuration of carbon atom is inverted. The change of configuration is called as Walden inversion. The inversion can be proved only if the reactant contains a chiral center at the reaction site. In such case, the product will have a configuration opposite to that of a reactant. Following experiment evidence supports the predict backside attack of a nucleophile and the inversion of a configuration in the product. The example, when R2 bromooctane is allowed to react with the sodium hydroxide under the condition where second order kinetics is followed, giving S2 octanol, we can see the reaction mechanism in the image given below. A reaction that yields a product whose configuration is opposite to that of a reactant is said to proceed with the inversion of configuration. In the above example, the product found to have S configuration, whereas a reactant have R configuration, indicated that there is an inversion of configuration. This supports the backside attack of a nucleophile. SNI reaction. This is substitution nucleophilic internal reaction. Most of the reaction proceed with the retention of configuration. The example in this category is a conversion of alcohol to alkyl halide by use of thionyl chloride. This reaction is carried out in anhydrous condition. This reaction involves the formation of intimate ion pair as an intermediate. When the same reaction is carried out in the presence of pyridine, results into inversion of configuration. Here ethyl alcohol is heated in presence of thionyl chloride. We get the product as CH3CH2Cl ethyl chloride with the evolution of SO2 gas and HCl as a byproduct. Here is the mechanism of the above reaction. It involves the formation of intimate ion pair, and it is an internal type of reaction. Elimination versus substitution. Both elimination and substitution reaction requires the substrate with the good leaving group, and the reagent should be basic and nucleophilic in the nature. In principle, there is a competition between the substitution and elimination. All elimination reactions are involved with the substitution product, and vice versa. Both the reaction result from the attack of substrate by the reagent. First, when the reagent acts as a nucleophile, it attacks alpha carbon atom from backside to bring out substitution reaction. Second, if the reagent acts as a base, it abstracts beta hydrogen atom to bring about elimination reaction. Here is in first case is the elimination reaction and alkene as a product of a elimination reaction, and in second case this is an example of substitution reaction. Structure of substrate. As the structure of the substrate become more and more crowded, percent of elimination reaction increases as one proceeds along the series of primary, secondary, tertiary. Then reactivity by E2 increases and reactivity by Sn2 reaction is decreases. Increased crowding in the substrate, the nucleophile is difficult to attack the carbon atom from the backside, that is Sn2 is difficult. Instead, it prefers to abstract beta hydrogen atom, leading to elimination product. Secondly, if the crowded substrate undergoes substitution, there is no relief from steric strain, but if it undergoes elimination reaction, the hybridization change from sp3 to sp2, that is formation of double bond, which increases the bond angle from 109 degree to 120 degree between the groups attached to carbon, and thus there is a relief of steric strain. Stability of alkene formed. If the alkene formed is stable, then elimination is favored more than the substitution reaction. We can see the more substituted alkene is stable here. The stability of alkene increases with the increase in number of alkyl group attached to that double bond, or it become conjugated to some other double bond. Stability of that alkene increases, and hence the chances of elimination is increases here. Next is the nature of leaving group. A good leaving group, however, promotes both substitution and elimination. However, highly crowded leaving group favors elimination over substitution. Thus, percent of elimination increases in order of leaving group ability. Solvent polarity. The transition state of elimination have dispersion of charges more than the transition state of substitution. Therefore, decrease in solvent polarity favors elimination reaction rather than substitution. The temperature also affect both elimination and substitution reaction. Higher temperature always favor elimination product over substitution. We can see the increase in temperature in the example given below favors elimination reaction with a 65% of elimination product and only 35% of substitution product. Summary. From today's session, we learn about nucleophilic substitution reaction, its mechanism, energy profile diagram, stereochemistry and kinetics. We also discussed about elimination versus substitution, how the structure of the substrate affects the elimination or substitution product. Higher temperature always favor elimination over substitution. A good leaving group promotes both substitution as well as elimination, and decrease in the solvent polarity favors elimination more than substitution. Thank you.